Hi everyone, today we're going to be looking at the apparent contact angle and how surface roughness affects it. So first off, the apparent contact angle is the contact angle of the liquid on any non-ideal surface. So any real surface, if the angle is greater than 90 degrees, that surface is considered hydrophobic, and if the angle is less than 90 degrees, it is considered hydrophilic. The Young contact angle is the contact angle of that liquid on an ideal surface. And these surfaces don't exist because the surface needs to be smooth all the way down to like the atomic level. So when comparing surface roughness and the apparent contact angle, we'll be using the Wenzo model as it is commonly used for hydrophilic surfaces. It is when the liquid penetrates the surface, and as roughness increases, the surface will appear more hydrophilic. The equation associated with this model is cosine theta W is equal to R cosine theta Y, where theta W is the apparent contact angle, R is this roughness ratio, which is the actual over the projected surface area, and theta Y is the Young contact angle. So for my experiment, what I'll be doing is increasing the roughness on a block of aluminum and applying one sessile drop onto the surface and then measuring its contact angle. The materials that we'll be using for this experiment is a block of aluminum, a pipette, some blue tape, some water that has been dyed blue, 70% isopropyl alcohol, and sandpaper of 180, 400, 600, 1500, 2000, and 3000 grit. So first, I've taped off 4 different sections. The first section I won't be sanding. The second section I'll be sanding with 180 grit sandpaper. The second section 400 grit, and the last section 600 grit. After I've sanded it, I'll be cleaning it off with isopropyl alcohol. So this is what the block looked like after I was done sanding it. So I then applied one sessile drop to each of the 4 sections and measured their contact angle. So this is what each of the droplets look like close up. Even before putting it in our software, we can clearly see that the not sanded section has a lower contact angle than the 600 grit sanded section. So after analyzing those 4 sections, I will now attempt to create a quote-unquote ideal surface or smooth surface. So I started sanding with 180 grit, then 400, then wet sanding with 600, 1500, 2000, and then finally 3000. I then cleaned the surface with isopropyl alcohol, then applied a sessile drop and measured its contact angle. So this is the sessile drop on our super smooth surface. I've measured the contact angle on the left and right side of the droplet to get an average. So these are the results from my experiment. The super smooth surface gave us an average angle of 80 degrees. The 600 grit surface gave us an angle of 75.5 degrees. 400 grit gave us 71 degrees. 180 grit gave us 61 degrees. And the not sanded section gave us 56.5 degrees. If we assume that the super smooth surface is an ideal surface and the contact angle that we measured on that surface is in fact Young's contact angle, and we rearrange the Wenzo model equation to solve for our roughness coefficient, we get a range from 1 to 3.178. Looking at our graph, we can see that as we increase our surface roughness, the contact angle that we can see does in fact decrease. In conclusion, we do see that as we increase our surface roughness, our apparent contact angle does in fact decrease. We also see that aluminum is a hydrophilic material, as none of the contact angles that we measured were greater than 90 degrees. It was pretty cool to me to see that this experiment worked as intended. And lastly, I want to address my super smooth surface and the assumption that it is an ideal surface. I understand that ideal surfaces don't exist, and there is some error involved when we assume that the angle measured on my super smooth surface is Young's contact angle.